Hi guys, we've started our chemistry unit now. Let's see if I can get this to work for me. I want the, what's going on here? There we go, that should get it up. No, come on, what are you doing? I'd like our slideshow in the background, that'd be nice, wouldn't it? But for some reason, in fact, let's try this instead. Drag that out of the way a bit. Don't drag any further. Hang on. I'll get this centered yet. Yes, now I'll try and drag it back. Okay, that's me. Hopefully it won't be a problem. So this is our chemistry unit. We just started our chemistry unit, and we're going to spend the next few weeks looking at a variety of ideas. Yesterday we started talking about the periodic table and elements, and today we've got some experiments to look at that, flame tests and pop tests and things. So in this little unit we're looking at the atoms, elements, periodic table, and in the periodic table we classify things as either metals, non-metals, or metalloids. Elements join together to make compounds, which happens through chemical reactions, and chemical reactions can take place faster or slower depending on what we do to them, so we'll talk about that too. And they'll finish with a little look at acids and bases, the pH scale, and indicators for working out whether something is an acid or a base. So, all matter is made of atoms, and we discussed the other day how the periodic table has each of these atoms listed in order of number of protons. So we talk about an element containing one type of atom only, and so the atom is the smallest unit of an element, although there are smaller things, and we'll talk about those later. We generally give an atom an English name, so in the case of carbon, it then gets the capital letter C as its symbol. But there are quite a few, like lead, which is called Pb. So it comes from its Latin name plumum. And so there's about 12 that actually carry a different symbol that you wouldn't expect. But generally we name them by the first letter of the name in a capital, and then if that capital's already been taken, so carbon's got C, cobalt became CO, and copper became Cu, and the second letter's in lowercase. They'll become really handy to know later when we start talking about chemical reactions. We talk of Mendeleev having having constructed a periodic table. And he certainly wasn't the first, and there were quite a few periodic tables around, but his tended to be the most accurate, and he was actually quite clever at being able to work out what he didn't know. So his original periodic table had lots of gaps, and lots of scientists have filled the gaps in since, because there are about 94 naturally occurring atoms or elements, and we've created quite a few since then, some of which are quite stable and hang around for a while, and others which are quite unstable, like the one we met the other day, Unum Septium, which is number 117. So that little diagram there is a bit old. But the good thing about it is, and the important thing about it, is that it organises groups of atoms into like characteristics. So you can see how it's all colour-coded there. And we did that little activity the other day and named each of those areas. So we had halogens and actinides and lanthanides and transition metals and all sorts of things. And those groups all have, and those colour groups you can see on that table, all have very like characteristics. And so the group with the far left-hand side with lithium, sodium, so Li, Na, K reading down the page, are really, really reactive. They've got one electron they want to get rid of. Well, don't want to get rid of, but they have trouble holding on to. And on the other side, we've got the group starting with FClBr, so fluorine, chlorine, bromine, iodine, and At. I forgot what At is. And they all want to gain an electron. And so these are also highly reactive. And everything else is in between. Of course, that last orange group, starting with helium, He, is known as the noble gases, because they have a full shell of electrons, and they're very hard to make react. They will react under certain circumstances, but it's hard to get them to react. So we talked about this the other day. We drew a nice big picture of a shell model, and you were able to tell me lots. Joey and Mia helped a lot with naming things, as did other people. So for each atom, is made of what we call subatomic particles below the level of the atom. And we call those electrons, protons, and neutrons. And each electron is made of smaller things again, and protons are made of smaller things again, and neutrons are made of smaller things again. We won't worry too much about those in Year 9, but there's actually subatomic particles too. And we know three really useful things about each of the subatomic particles. We know what charge they have, we know what position they have in the model, and we know how much mass they have. So, an electron has a negative charge. It exists away from the nucleus of the cell in these shells of energy, and we suggest it has no mass. That's not quite true, but for our purposes that's enough to say it has no mass. Protons are positively charged and found in the nucleus, and neutrons have no charge and are found in the nucleus. And they each are said to have one atomic mass unit. They don't weigh a gram, they weigh a lot less than a gram. So we've made up our own units for these things, and we call them mass units. So when you're looking at your periodic table, you'll see two numbers beside the symbol. The first number is the atomic number, and it tells you how many protons that the element has, which is also a measure of how many electrons it has, because the positive and negative charges have to be balanced. And the bottom number is generally the mass number, and that's the number of protons plus the number of neutrons. So there's a lot of information held in the periodic table, and it's very useful to be able to refer to it. And the periodic table tends to have three main groups of things. We saw those color-coded groups before, but there's three major groups: the metals, the non-metals, and metalloids. So metals we know quite well. Most of the periodic table are in fact metals. And we say they're usually solid at room temperature. They are often shiny. We can shape them into jewelry and pendants and all that sort of things. So we can make iron rods and buildings out of iron. So they're malleable. We can make shapes and they hold that shape. We can also draw them into wires, and they stay drawn into wires. And those wires will usually conduct heat and electricity really well. So copper is fantastic for passing electricity around the place, moving our hot water from our hot water service into our taps, that sort of thing. The non-metals are the things that aren't metals, if you like. And they have all the opposites to metals. They're usually gas at room temperature. They don't conduct electricity and heat particularly well, although they can be made to, and so that's one of the really useful things in our electronics, like our telephones and our computers, that semiconductors can be switched on and switched off to conduct electricity, which is quite useful. They're often very brittle, so when we use sulfur in class, it's always in a powder form. And because of these characteristics, they can't be drawn out into wires or made into jewelry. They just don't hold the shape. And in between the metals and non-metals are a small group of things called the metalloids. They've got sometimes they're a little bit metal-like, sometimes a little bit non-metal-like, but they're not both. And apparently, those all fun facts, a thing called astenine is so rare they reckon there's only 1/3 of a gram in the Earth's surface. Don't ask me how they made that calculation, but apparently that's what they suggest. So elements normally don't hang around as pure elements. They tend to hang around in molecules, which are the smallest units of a compound. So in our table here, we've got compounds that are made of one type of atom only. So hydrogen, oxygen, nitrogen, and chlorine exist as elements, but in our world, we call them compounds because they don't exist as single atoms. They exist as compounds of many atoms. And then, of course, we've also got compounds which form between different types of atoms. And so that little diagram there's got nitrogen oxide, water, nitrogen dioxide, carbon dioxide, carbon monoxide, all those sort of things that we're quite used to hearing about. A number of atoms joined together. There's a formula to it. So water is always 2 hydrogens to 1 oxygen. Nitrogen dioxide, 2 oxygens, 1 nitrogen. So there's always a formula to that compound. And that's quite important for when we start doing reactions and trying to describe what's happening. To form compounds, chemicals have to react together. So when we take 2 compounds, let's say we take hydrogen and oxygen, they would be our reactants. They react together to produce a product, water. There's some names you need to be aware of. And of course, as we talked about before, the noble gases are quite hard to make react, so they don't like reacting with anybody. And some chemicals don't react with each other very well at all. And that periodic table can allow you to work out whether two things may in fact form a compound or not. And so chemists obviously like to know their periodic table well and like to refer to it all the time. Chemical reactions, we talk about them being physical or chemical changes. So in a physical change, no new substance has been reduced. So my classic I discussed the other day is good old bread turned into toast. Once it's toast, it's not going backwards. Whereas chemical changes can be undone. So if you've had a chemical change, you can normally reverse that. So if you started with hydrogen and oxygen and made water, you can in fact cause them to come apart again and become hydrogen and oxygen. So a chemical change, with a bit of effort, can be caused to be undone. How do we know a reaction's taken place? Well, we get a lot of gas, so you can see bubbling up in your test tube. We might get lots of light or heat given off, like that explosion in the picture. We might get a change of mass, so we might have started with 5 grams and at the end we've got 10 grams. Or we start with 5 grams and at the end we've got 1 gram. So we've lost or gained mass somewhere. We could get a complete change in colour, and we'll do some of the experiments soon and you'll see all these things happening. Or you might form what's called a precipitate. So you've got 2 clear liquids and all of a sudden there's a solid at the bottom. And that's fallen out, that's precipitated out of the solution. One of the really important people often called the father of chemistry is Antoine Laurent Lavoisier, who developed the law of constant mass way back in the 1750s, and it still holds, so it's a pretty rare thing. And unfortunately, because he was an accountant and a tax collector, when the revolution came, they killed him. They took his head off with a guillotine. But he's very famous particularly for the idea that matter is neither created nor destroyed, rather is simply transferred or transformed. And this becomes really important when you try and balance an equation. Because he realized, being an accountant, that what the reactants he started with had to be able to be accounted for in the products at the end of the reaction. They just don't disappear, they've gone somewhere else, they've changed them around. And so he's very, very famous for that, amongst other really important bits of chemistry. And he was an amateur. He was actually an accountant by day and scientist by night. It's his hobby. Reactions can be made to go faster or slower. So the temperature changes a reaction quite a bit. So the hotter it is, the faster it goes. The colder it is, the slower it goes. I can make them more concentrated, so really concentrated acids work much faster. I can make the size of the particle much bigger or much smaller. The bigger it is, the slower it reacts. The smaller it is, the faster it reacts, because there's more surface area for the chemicals to work on. We won't look at catalysts this year, but we can use a chemical called a catalyst, which also helps get things going faster. We're also going to quick look at acids and bases. So acids are a group of chemicals, and most things can be measured on this pH scale and are either acid or base. We know them from our food. There's things that taste sour, so that lovely sour taste means you've got an acid of some sort in your mouth. And quite a lot of naturally occurring. We have them in our digestive system to break down our food. Our food contains acids. And it's only really a problem when we have too much acid in a place. The opposite to them are bases, and again we use bases a lot to clean things. They're very good at cleaning. They have a bitter taste or a soapy feel, and if you get them on your fingers, you'll find your fingers go really soapy. And again, they're also found in nature a lot, but when they become too concentrated in the wrong place, then we find that they become a problem. If you put an acid and a base together, they tend to neutralize, and that we get this lovely equation where acid plus base will produce some salty water, basically. So salt's just suspended in water. So if you've got a problem with an acid, the best way to fix it is with a base. So antacids for people with indigestion are bases added to cover the acid that's coming out of your stomach. We talk about being able to measure this on the pH scale. And pH essentially stands for the strength of the hydrogen, the portends of hydrogen, as a Danish scientist, I think. And so your stomach acid is around that 1 over the battery acid level. Vinegar you put in your chips is around 2, so they're quite common. Ammonia, which you might use to clean things, is 12. Milk, human blood, is around the neutral, around the 7. So 7 is sort of neutral. So everything can be measured on this scale, and we measure that with indicators. And we'll use a whole range of indicators in class to see how this works. So they can be paper-based, they can be chemicals, or in fact you can use probes now. We've got all 3 we can use. And I've just managed to fit that into my 15 minutes. So that's chemistry. We're going to have a lot of fun over the next few weeks. I hope you enjoy it. See you in class today.